The next item is FRP design. This is the actual design that we must use for FRP consistency. So what I did until now is I presented you the basis for ACI 318 and I compared it with IS 456. So you see the difference. Now I will introduce you to ACI 440.1 requirements for fluxural members. Is that okay? So is this a good time to take a break? Or it's a FRP fluxural design. Some of this is repetition, so we will just skip it. Not go into too many details. So the design method is very similar to steel reinforced concrete sections. The only difference is we have linear stress strain curve until failure. That makes it a little bit more tricky. So we need to consider that. And the equations are mostly valid for rectangular sections because they were derived, and the testing, in most cases, the testing is done with rectangular sections, small beams up to maybe 10 meters or something like that, very small beams, small beams. So the design equations have been all derived based on small tests with rectangular sections. Therefore the equations are mostly valid for rectangular sections. However, it is possible to use those for other sections like T sections and all, but the test results are not available for that kind of sections. And then most research done so far use tests with one layer of steel or FRP bars, one layer of FRP bars. If you have multiple layers, maybe 2 or 3 layers, you can use strain compatibility method, but there are not that many test results in available to compare. But it's okay to use these design equations for other conditions as well. So structural design philosophy, we already have this covered. So we prefer over-reinforced failure mode. And FRP reinforced concrete beams will have slightly smaller ductility, therefore you have to be using larger safety factors or smaller strength reduction factors. And over-reinforced section is more preferred than the under-reinforced section. Okay, the assumptions are the same, or at least similar. Plane sections before bending remain plane after bending. That's something we are familiar with. The result of that assumption is our strain diagram is linear in shape. Epsilon CU is 0.003. Tensile strength is ignored. Linear elastic stress strain curve for FRP bars. The other thing we assume is there is perfect bond between FRP bars and the surrounding concrete. That may make a difference, because sometimes the design is governed by bond rather than the tensile strength of the bar. Sometimes that can govern your design. So in any case, phi mn should be greater than m sub u. Phi mn is the design moment strength. M sub u is the required strength or the factory load effect. So this is a basic requirement. We will satisfy this in all our designs. And then we will use strain compatibility, equilibrium of forces. Total compressive force should be equal to total tensile force. And then we will base our design on over-reinforced condition, in which case the concrete will crush first and then the FRP bars are likely to fail. So if you see the stress strain curve and the corresponding stress block, this is what it will look like. We have a rectangular section here, width B, effective depth D, strain diagram with epsilon Cu here, which is equal to 0.003, and epsilon F here, which is the strain in FRP bars. If it is over reinforced condition, we will reach epsilon Cu of 0.003 first. Does it make sense? Over reinforced condition, right? And then this strain will be smaller than the failure strain. Make sense? Very important to remember that. So because we have already strain of 0.003 here, we will have a fully developed stress block, which is in ACI approach, it's just a rectangular stress block. Once you have a rectangular stress block with uniform width, the total force is at a distance of A over 2 from the top. And of course, this is beta 1 times C. Beta 1 depends on F prime C. And at the bottom, the force is AF times FF. So now I'll ask you a question. Make sure you're all awake. So, do I know FF? Okay, that means I did not explain very well. I will explain it again. So this is an over reinforced condition. Okay, what is the meaning of over reinforced condition? In over reinforced condition, the failure is by crushing of concrete. So this strain will be 0.003. What about this strain? That strain is not yet epsilon Fu. It is smaller than epsilon Fu, right? If it is equal to epsilon Fu, then what do you call that condition? Balanced condition. Very good. So we have over reinforced condition, therefore this strain has not yet reached epsilon Fu. Okay, makes sense? So if this is not epsilon Fu, what is it? It is epsilon F, which is smaller than epsilon Fu. Therefore, at this stage, my question back to you again. Do I know FF? No, we don't. Does it make sense? Yeah, at this point, we don't know FF. So, we will have to write down compatibility equations and solve for FF. Okay? Very good. So, what about balance? Can you already answer that question for me? So this is 0.003 and this is defined. This is a defined value of epsilon Fu, which is guaranteed tensile strain. Remember I said we are going to use guaranteed strain somewhere. So we'll start using that. Epsilon Fu. And now I'll ask you the same question. Do I know the stress in the FRP bars at this time? Yes, because this value is epsilon Fu, therefore the stress at this point, at this condition is Fu, which is a known quantity. Very good. What about the third condition, under reinforced condition? First of all, let's go back to the section. It's a rectangular section, you have bars here, that's D, fine. This is the strain diagram. This strain is how much? Oh, you made my day. That's correct. This is less than 0.003. Less than 0.003. And what about this strain here? Oh, it's it will be at the limit. It will be epsilon Fu, right? That means we are ensuring the failure. Not ensuring, but in this condition, it so happens that the failure is by rupture of FRP, and therefore that's the limit strain. Now, epsilon C is unknown. It's not 003, not 0.003. That's an issue, right? It's a problem. So, if you go back to our stress strain diagram, if you see IS 456 stress strain diagram, we have parabolic condition and then we have, let's go back. I want to show you what that is. You know it, but I just want to discuss something. Not here, I think it's in the other one. 10, 9, 8. I just want to remind ourselves what this one here. Right? So here up to 0.002 we have parabolic variation. Beyond that it is straight line variation. So if my strain is, let's say, less than 0.002, then I need to consider this parabolic shape as my stress block. Is that right? If my strain is between 0.002 and 0.0035, then I need to consider that here. So I will have a rectangular stress block and a constant parabolic stress block up to 0.002. If my strain is 0.0035, then I have all the parameters. So if my strain is less than 0.0035, it can be less than 0.002 or just less than between 0.002 and 0.0035. In that case, will the total force still be 0.36 FCK XU? Will it be or won't it be? Let's go back to the basics. This 0.36 FCK XU is based on this of 0.44 FCK, and this uniform stress between this level here 0.002 and 0.0035, that's a constant value, right? That area is constant, and then this area is also constant. But now I am truncating depending on my maximum strain at the top fiber. My stress block may be up to here, up to here, up to here, or up to here, nobody knows, right? In which case this total compressive force of 0.36 FCK is not matching. You need to find out the corresponding area. If it is a uniform width section, if it is a rectangular section, you need to find out the corresponding area of the stress block up to that point, right? So that becomes a little bit tricky. So designing an under reinforced section in case of FRP reinforced beams is more complicated. It's not that it cannot be done, but it's more complicated. Yeah. So that's our under reinforced section. So this strain here is less than 0.003 or 0.0035 in case of IS 456. You may have just a triangular, or in IS 456 you use a parabolic stress strain curve. So if it is very, very small, if epsilon c is very, very small, you probably will use a triangle. If it is larger than about say 0.001 or something like that, then it starts becoming parabolic, right? So this area is not known, and therefore we cannot use rectangular stress block. You can use a rectangular stress block only if strain is equal to 0.003 or greater. If it is not yet 0.003 or greater, you cannot use a rectangular stress block. However, ACI 456, ACI 440.1 has actually said that they have validated and verified, and they said you may be able to use this depth to neutral axis as balanced condition, okay, and use the rectangular stress block corresponding to the area of the FRP. So it's not perfect, it's an approximate approach. For quick calculations, this is quite useful. Okay, for more detailed calculations, you must use strain compatibility method, which I will be presenting after the break. So for under reinforced sections, we will use an approximate design equation given by ACI, and then we will calculate our moment strength. So this one is I mentioned most of these, so I'll just move on. So for balanced condition, all that you have to do is assume this strain to be epsilon FU assume this to be 0.003 and then find out the depth of the compression block. Of course, first you will find out the depth to neutral axis and then use beta 1 to find out the depth of the compression block. Is it making it easier to understand now? Because we already talked about the basics in the previous presentation. So it is very simple and straightforward now because we understand this really well. So first thing you will do is draw a strain diagram. And the strain diagram for a balanced condition will have strain of 0.003 here, 0.00 or epsilon FU here. Epsilon FU is based on the actual material property of FRP. So you draw a straight line. So that will intersect this vertical line somewhere. And just by similar triangles you can find out C. Once you find out C, you can calculate beta 1, and if it is if your compressive strength is less than 27.58 or something, that's like 0.85. Beta 1 is 0.85. Based on that you have this depth, right? Beta 1 times C is this depth. We already found out C from this similar triangles, right? So that's your beta 1 C. So once you know this depth, our average stress, remember this is one thing you might want to remember. The average compressive stress in fluxural compression is always 0.85 F prime C. If you remember that, you don't even need to go through the ACI 440.1, nothing. You don't need to see anything, look at anything. Just from your understanding you can calculate all this. So this is beta 1 C, and then once you know the depth, you know the width, average stress is 0.85 F prime C, therefore area is A times width B, which is this here, and that will give you the total compressive force. The corresponding total tensile force is AF times FFU. So you can calculate your movement strength based on this. Does it make sense? Very good. So whatever I said until this point, I just wrote it down here. So I have beta 1, I have an expression for AFB, which is the area for balanced condition, area of FRP for balanced condition, and you will see, let's say everything is the same for a steel reinforced beam and FRP reinforced beam. You have area of steel is same as area of FRP bars. In that case, what would be the effect on AFB? What would be the effect on AFB? So let's look at the equation. This can be derived, okay? It's just based on equilibrium. So 0.85 is a constant. Beta 1 is dependent on F prime C. So in both cases it's the same thing, right? Beta 1 for same concrete, it will be the same for both cases. F prime C is the same, but this stress is not the same. That FFU is very large. Are you agreeing with me? Because it is larger, this FFU is larger than the strength of steel, which is Fy. So let's say the factor is 3. Then you have epsilon Cu over epsilon Cu plus epsilon Fu. Here also this is large. Epsilon Fu is large compared to 0.002 or steel yield strain. So we have a large quantity here, and you have a large quantity in terms of FFU. So what happens to AFB? It will be very, very small. Very, very small. Compared to steel, it will be almost 1/4, 1/5. Very, very small. If you want to